Benjamin, and thank you, Zara, for your invitation. I just got the notification that now I'm being recorded, so that's great. So today I'm going to speak about a paper that we're essentially going to submit. It's a matter of days now, so it is finally completed, and it's some of my work joined with some of my students. It was David Liver and my former postdoc, because she finished now. I don't have the name here, Zara Mohammadi, who is a postdoc actually in MFPH until this summer. And then my colleague Mihai Nica, my colleague Ed Thomas, and then two French colleagues. Giacomo Cacciapoglia is a professor of the INRS in the University of Lyon, and Corentin Cott, who was his postdoc at the time when we started the work, which was about a year ago, and I was a postdoc in physics at the Université de Paris. So what we've been working on is sort of in the title, it's a long title. So we had some proprietary data on population mobility, and the mobility not in the sense of Google mobility or Apple mobility, but much more sort of granular than that. So it's really to the level of the US. So the data is from the US, and is granular enough to track essentially a flow of people from county to county. So that's it's captured by a specific vendor, and it came to us courtesy of our collaboration with Sanofi in the US and in Sanofi Global. So what we've done with this, let me just give you a quick update on the talk. So I'm gonna introduce you to how we came about with the ideas you're going to see. We're going to essentially use this mobility type flow data to create a reclustering of the US population, and we're gonna have some very specific, simple optimization-based clustering objectives. We're going to talk a little bit about what we get after we apply our brand new sort of newly designed algorithm, and what we call by clustering stability. We're going to then talk about what is the significance of this particular methodology when we view, for instance, the recasting of populations in these smaller subpopulations with specific specific constraints, let's say, specific desired traits. What is the epidemiological analysis viewpoint on these? We're going to talk about whether or not this newly revisited epidemiological analysis for the beginning of the pandemic, so the first half of 2020, will give rise to some interesting regional analyses and policy implications, specifically by policy implications, meaning at the time, remember, at the beginning of the pandemic, we didn't know much about things. Everybody was quite scared and panicked, and of course, non-pharmaceutical measures to try and flatten the curve and stop the spread were really the main things that we had as our tools. And then we're going to touch upon at the end and model usability, and whether or not this actually does constitute a modeling framework, meaning you can take the mathematical algorithmic sort of implementation and just put with different types of data, with different types of regions, is it still usable, is it still useful, and whether we can do this, and we conclude that we can. So and then we're going to have a brief summary for that. So during the pandemic, I should say that people can stop me from, if they have questions at any time. I will not be able to see you because I don't know, my tiles here for my view have become very small. But Ben perhaps or Zara can flag me if I have a question and I don't see it. So during the pandemic, of course, we are all now very familiar with, we became all of us very familiar with what I call traditional modeling of infectious diseases, and that's generally via ordinary differential equations. And so those are very, very powerful. Many people have used them and they've been extremely useful. We also have encountered a huge amount, unprecedented amount of data, a lot of it free and some proprietary, such as like the one we have used here, specifically on various things, but narrowed down to people's movements. So the way they stayed home or didn't stay home, social measures, economic measures being implemented, behavior captured for people, mask wearing, and so on, right? So one of the larger questions, of course, in all of this, now that we're looking back and, sort of looking somewhat more critically, perhaps, over what happened to us, is how to best use this large available data in equation-based or otherwise any other types of models, stochastic models, probabilistic models, and so on, or agent-based models. And when we look back and we try to see, what we've been through, the idea is always, I guess, at least in our group, is always to, yes, we can use COVID data. Yes, we should probably use it because we had so much of it. But what can we draw? What conclusions can we draw out of what happened to us, if at all? So in a traditional regional approach to infection spread, for instance, and this goes back to early works or early 2000s, even late 1990s, from Pauline van der Drisch and co-authors, for instance, Juliana Arena's one and others. There are a bunch of models where regions are modeled essentially by their own set of differential equations. So you would have a compartmental model, right, modeling that particular region. And then, of course, then there's extra terms to account, say, for people traveling or people being mobile between various regions. So the regional division of populations, of course, is nothing new because we all have it in every country. There's the census data and for instance, public health regions, counties in US, public health regions in Ontario or Canada. And how these came to be depend on each country's socio-demographic, historical, and and census type of data, right, and criteria. So in general, SIR, for instance, models, compartmental models, right, work really, really well for large populations. And this is because, of course, the fundamental assumption underlying the ODEs, these particular types of ODEs, are that in each compartment, the populations that we're looking at there, the susceptibles, the infected, the exposed, and so on, are well mixed. In other words, they're kind of not really that different between one another, right? And so it kind of works very well at the country level. The bigger the population, the better it works, so to speak. But when you come down to more granularity and regionalities, you have smaller regions, smaller geographical patches, then the populations are smaller, and the data that you might have locally is also smaller numbers, right? So we're running into small number statistics. And then these assumptions that each region might have an SEIR attached to it is becoming a bit more problematic, not to mention that, of course, the size of the model grows, right, quite enormously. As you know, the more subregions, the more collections of these SEIR models you have, the more complicated it is to model them. So what we did is we said, okay, let's not worry so much first about the, the modeling, the transmission with traditional SER models, patch models or population, but rather let's look at what we have, which is this mobility data essentially between counties in the US. And then let's recluster the US population with two criteria. The first one is we want to obtain subpopulations of clusters, of subpopulations that are, given our data, the mobility, the way that people move around the counties in a new cluster is much larger than the way people move between the cluster where they were put in and another cluster. In other words, we're minimizing mobility between the new cluster. So we want less flow in and out between the new clusters, but a lot of flow mobility inside each cluster. And then we also want to have, population sizes, and the way we recast in these clusters of subpopulations, we want the population sizes to be not enormously different, right? By that I mean, if you remember, we're talking about the US. So in the US, we have states, for instance, like Montana or South Dakota or something, where the total population is somewhere, under 500,000, probably less than that. And then we have states like California, where we have millions, right? Tens of millions. So we wanted to not have that particular feature in the new clusters. So then let's say we minimize a difference in population size between clusters. So with these two specific criteria, what we do is we do a clustering algorithm, right? And then we have these loss functions. So we're going to have a loss function due to interactions, interaction meaning mobility, right? Outflow between counties and nearby counties. And then population loss in a sense that we're trying to not have very small populated clusters and not very large ones, right? We don't want to have like one giant cluster to be the entire US. That's beside the point of the model. And so, of course, then the total loss, let's say, of which we're trying to minimize, obviously, is going to be a combination of the loss from mobility and the loss from the difference in population sizes. So how do we do this? So we can give ourselves a number called n clusters. So this is, we choose this number, right? So you will see in my simulations, for instance, we started with 100 clusters. Then we're mostly worked with 49. Why? Because in our algorithm, this n clusters, we like it to be a perfect square. And the number of US states is roughly 51. Now, Alaska is always going to turn out to be a cluster on its own. And so we're sort of down to 50. So 49 is fairly close to 50. And then the number of regions we are clustering really, these are not regions, these are the US Census county, right? Counties, which are 3,000 and some in total in the entire US. So using this data, we create a probability matrix P in such a way that each element in P is a probability that a node I is in cluster J, meaning the probability that a county, the node, right, a node is a county, the county I is in some cluster J. So we do it this way, and then we want, of course, to sum up to 1 in the entries of the P matrix. Okay, so now what do we do with this? We have the two loss functions, so to speak. One would be the so-called interaction loss, so this is based on mobility, and the other one, the population size. So by interaction loss, we have interactions between clusters measured in terms of mobility of populations between counties, and is based on the availability, which is proprietary, of county to county inflow and outflow data. We use the outflow for this, using the below formula. And so the below formula sums the expected interaction over all possible pairs of nodes, right? And so, I mean, I'm not going to launch too much. It's a very simple matrix algebra, P different here. So is the probability of node I, county I, to be in a different cluster than county J. And then by simple matrix operations, this can be expressed as 1 minus P times P transpose entry IJ. And I don't know what happened to my symbol here in formula 6. This is supposed to be a thicker, bold, big 1 to signify a matrix with all entries 1. So I'm not sure what happened to my symbol here. So essentially this loss interaction, we're looking at the trace of this matrix, the interaction times 1 minus P times P transpose. Oh my God, I apologize. My computer is having a hiccup. The population loss term forces the algorithm, we like to force the algorithm to produce clusters of approximately equal populations. And you can see quotation marks, of course, they're not going to be equal, but what I meant was to not have these very big differences in population in clusters. So this would be, we're summing essentially over the difference between the expected population in a newly formed cluster minus the total population in those counties that we amalgamate together over the total number of clusters. And we square that. And with some more simple algebraic sort of manipulation, we can write this loss population part of the function as, again, in matrix form. And P transpose population minus this sort of term. So, okay. With all this being said, so we've done some essentially probabilistic view of a kind of an adjacency matrix, if you think about it, of mapping counties to new possible clusters. And so what are we trying to do? What we're trying to do is we're trying to find this matrix P, right? And so we're trying to find the matrix P, which in general, of course, has this condition here that when I sum for each row I, when I sum between J from 1 to the number of clusters that I want to obtain, say it's 100 or 49 or 25, whatever, these sums have to be 1, right? Because this is a probability matrix. Now, generally speaking, when I want to say, oh, I want to maximize the loss function in such a way, you know, I want to solve for P in such a way that I minimize my loss, but subject to these extra conditions. So this is a box constraint in optimization terms, and this is a linear constraint, a bunch of them in optimization terms. So generally speaking, in machine learning, right, which are very, very good to do this kind of sort of, optimization and reclustering of data, we love to use the gradient descent, right? But the gradient descent is generally very, very good, somewhat slow, but very steady for unconstrained optimization. If I try to apply it to P, this is not unconstrained because I have constraints. So I would need some sort of projected gradient descent method, which people don't really like in machine learning. They just like the gradient descent. So in order to basically not have a constrained conditions on P, we essentially use a trick that people use in machine learning. So we're really solving for a matrix X. Now X is unconstrained. And then after we solve for X, then we retrieve P from X by essentially a softmax function, right? So in other words, we posterior, so after we compute X, we kind of try to apply this sort of constraint, right? And then because X now is unconstrained, then we basically just go at it with a gradient descent type of method. Okay, so we've so this is the slide that I was just explaining, how we went from P to X. And so now in terms of the algorithms, the algorithm that we design, the initialization of X, right? So in other words, to start the algorithm, we have to start with the 3,000 plus counties in the US and randomly assigning them in some clusters. So we can do that randomly. So random assignment. Let's say I want to obtain 100 clusters at the end. And I'm going to randomly start assigning, my 3,000 something counties to 100 clusters. Whenever we do this, of course, we don't know how good of or how far is our randomly obtained initialization of clusters, how good it is compared to where we need to go, right? How the algorithm, what is a good enough solution of the algorithm? So we could be very far. In other words, we would need to run the algorithm many, many, many times over, or much longer. So therefore, in order to not do this, we came up with a, let's say, speedier way to start the original assignment. We call it the distance to centers. So we have some Euclidean distance, or literally just on the map, from the center of each node to each other node. So the node will be the states or, subdivisions and states. So we have 50 states. We have divided roughly by 2 will be about 100 patches. And then we're going to go from the centers. So it's another way to construct an initial number of clusters with nearby regions. Okay, so it's very, very simple. And for instance, to show you what we get is something like this. So let's say we want 100 clusters for whatever reason. And then we start from our, very regular map of the US. And if you see here, like these white patches, they mean essentially that we didn't have data. We didn't have data in these particular counties in our data file. So we don't know anything about the flow here, but there's very few patches like that. And then if we run our algorithm, we get our 100 clusters with the 2 conditions that we want. So you can see they're very nice, colorful, a little patchy, right? There's a lot of conglomeration of colors. But the point of this is to show you that we can do it, right? We can give ourselves a number of clusters and we can recluster the population according to our 2 criteria. And to convince you that the algorithm is working, we're looking at this figure here, which is a heat map of mobility interaction between clusters. So for instance, this is a map for 49 clusters. And so we checked to see if indeed the end result, the 49 clusters that resulted when the algorithm stopped, if the mobility data in those counties that were clustered in the 49 clusters, right? If the mobility data has a spike up, so it's a lot of mobility internally, right? So they would mean that the mobility tracer should be higher on the diagonal and should be much lower off diagonal, meaning, for instance, cluster 20 interacts the most, right? Mobility-wise, outflow and inflow interacts the most with itself, cluster 20, and not with the other guys. Okay. Now, to reassure you that we're not, just pulling this out of thin air, we have asked ourselves 2 questions. One is, have other people done this kind of thing before? And to the best of our knowledge, the answer is not really, no. People tend to do clustering of population in some populations, but they use similarities to actually cluster things together. We use differences and minimization, which is a different approach. But nevertheless, there are many established, especially in statistics, established clustering algorithms that people have been using for many years. For instance, the stochastic block matrix algorithm. And we compared our results and the functionality of our algorithm here with a stochastic block model. And, you know, the comparison was pretty good, was pretty solid, meaning we're not getting weird results. We're not getting off the chart, you know, things that other very well-established algorithms tell us that we shouldn't get. Right? So that's like sanity check sort of in the background to make sure that what we produce is actually reasonable. So what have we done with the algorithm? So now we have the US, we have lots of data for the US, which is free. For instance, incidence data, right? In every county, in every state. We have this proprietary sort of mobility data, which we've already used to cast the clusters. So the interesting thing is we can do this, we can run this algorithm and produce clusters, say 49 of them, right? Because it's closest to 50 states. We can produce these clusters anytime we want. We have data to the level of weekly throughout 2020. So for instance, each week of 2020, we can start and then, you know, produce some sort of 49 clusters. And the question was, what is the degree of changes in clustering from week to week? I mean, because then, you know, how do we quantify what is relevant over time, right? Things change over time, policy changes over time, diseases spread over time, people's habits or mobility changes over time. So this clustering and reclustering of populations could only be useful to us if we find a measure of consistency, right? Between a clustering that is spit out at me for middle of week 2 of January 2020 and week 2 of March 2020, for instance, and week 2 of May 2020. Like, but you know, what if anything can we say that is sort of similar in the structure of these clusters, and what is different? So we worked quite a bit on this, and we define what we say a measure of consistent clustering. So it's a matrix that determines the probability of two nodes belonging to the same cluster over and over again. So if I, you know, cluster, I do my algorithm every week. And if I observe that there is a bunch of counties that always get clustered together, right, over time, that should imply that there is a clear measure of consistency of intermobility in that cluster between these counties. And we should actually flag this, right? Because without this, we cannot really say anything relevant about the epidemiology analysis later on. So what we ended up saying here with this analysis, we saw that some counties flip-flop. We used to call them that. We used to call them flip-floppers. In other words, they would sometimes belong to one cluster, then other weeks would belong to a slightly different cluster. So there was no particular stable assignment, but there was a lot of counties that were repeatedly clustered together over time. It didn't matter that it was January, March, April, or June of 2020, which seemed very interesting. So we defined these to be core clusters. This is the mathematics of it. It's, again, matrix analysis, very, very simple. But I want to give you the picture. Picture is worth 1,000 words here. So here we said we're going to cluster the US population in 49 clusters. And if you see what we've done is we've done it, I believe, every 2 weeks between January and June. And we discarded the light gray counties, right? These light gray counties are the flip-floppy ones. So the ones that are, get assigned and reassigned in different places. It's not clear where they belong to. And in turn, we kept what we call the core clusters. So if you see the core clusters, right, they look fairly sort of interesting, a lot more like clear. And what's interesting in this is that you can see here, it says these are core clusters for an interaction threshold of 0.25, right? So what does that mean? Well, if we, the definition of a core county or a flip-flop county will really depend on how we internally define the threshold of difference between a matrix M1 and a matrix M2, where these are two different clustering at two different times. So a threshold of 0.25 amounts to essentially excluding about somewhere between 5 to 10% of the US population, right? Specifically in these light gray counties, while retaining the other 300 and a bit million, right? So we figured that this is not a bad loss, but more importantly, why we specifically narrowed in into this picture, because we have pictures, for instance, for a smaller threshold, so there's less flip-flop, right, and more core, or a higher threshold, and then there's even bigger discounted areas. But this one particularly is very, very similar to the map of the USA, specifically the map that depicts urban and rural populations. And in fact, a lot of these flip-flopping counties, for lack of a better word, the inconsistent ones, right, are along the lines of rural areas. So this was very interesting because, we all know that, of course, in theory, population density is very important in disease transmission. And we know that. This way we see it right away by construction, so to speak, just looking at how people move on a regular basis. To convince you that our cluster, the core clusters, the non-light gray areas, the colored ones, really do what we said they're going to do. Is if you look here at the population of the US, right? This is in millions of people. So this is the histogram of the population size of US states, right? There's some very largely populated and some really sparse. You can see in our clusters, the population, the histogram is a lot flatter, right? So we kind of achieved that other second criteria where we want clusters to be, populations to be not so widely different in size. So then we look at epidemiology. And so now remember, we have 49 clusters, and then we have some flip-flop counties, the light gray ones, which we're just going to discount that population, very sparsely populated. We're going to look at the core clusters of those, and those are the stable core clusters over time. So throughout January to June of 2020, these are kind of consistently together, consistent clusters. So if we now, with this in mind, if we now look back and look at the epidemiology of what happened in the US in the pandemic, we can of course compute, for instance, the R0, right? And this is the one way that we did it from data. There's many other ways to do it, but we wanted specifically to use data and not so much other estimates from like published models and so on. So what we did is we assumed that the near disease-free equilibrium, which is a very classic assumption, the incidence increases exponentially, right, when it takes off. And that means that this growth factor rho, which is the power of the exponent, is actually, we can find it from data, right? So is the ln of the incidence today minus the incidence yesterday, at the very least, if the incidence yesterday was not zero. And then the reason why this is such a great computation is you can use direct data to deduce rho with some packages in R. And then you can use well-established literature from Professor Junling Ma and some co-authors in Alberta, where they show closed forms expressions of how R0 can be computed based on known values of these growth factor, the exponential growth factor, near DFE. Okay, so we used all of that to compute these two maps. Okay, the upper map is the state level, so you can see all the states. We don't have Alaska here, but again, it's on its own. So this is the state level R0. And this is in the first few weeks, I believe, the first 4 weeks of, we used the first 3 to 4 weeks, whatever the data really started to take off in each state. And so these are the counties and states. And so you can see the yellow, the more yellow is the higher R0, and the more darker blue is the lower R0. And we've done the same by looking in our clusters, the counties remaining, right? And the counties that were clustered in our consistent clusters over the same time interval. And we did the same computation with the same color map. And so if you sit and think, it's like, okay, so what can we see here? It's perhaps not so obvious, but to make it more obvious, then in the next map, we just took the difference of the values we got here in the state level and the values in the county level to try and highlight what you would say. Well, I would say we're trying to highlight the difference in computed values between the geographic census dictated state type epidemiology, which we've seen over and over and over again, and the consistent clustering epidemiology, and trying to figure out if we see anything interesting. So if you do the difference, we can immediately see some important differences, specifically here in the Northeast, right? So this area here, we have R0, that is the difference in the R0s it's quite big. This seems to indicate that, for instance, here there are swaths of counties where previously in a statewide type of statistics, it's right here. This was like, oh, this is safe. This is great. We don't have a lot of cases. We're great. But in actuality, the situation was not great at all. It was the other way around, right? Because people movement and interconnectivity in the R0 was higher than the one looked at state level, and the same all the way in this corridor here. So this is use number one of how recasting the population tells you a lot more granularly what actually happens and why sometimes doing the state analysis is not the best way for figuring out what to do. This next figure is probably my most favorite result of this entire paper, alongside with the rural areas that just show up to be discounted naturally, right, because of low mobility. This is the clusters, so 49 clusters. This is the weeks of February 24 to March 16, so 4 weeks. Red indicates that is the region that lights up. In other words, is the first time when R0 can be computed. And later on, the gray is the untouched, so there's no infection. The light gray are the discounted counties, right? And then the green ones are counties that were red, so where the infection started and now is like full on going on. Okay, so if you look at the timeline here, it's very interesting because, of course, we start in the West, as we knew. And the next one, the upper top, the upper right panel is the most interesting, I think. If you look carefully at where the next light up areas show up between very early on the West Coast to a week later, this is just a week later. If you see something interesting, these red patches of counties are all around very big airport hubs. This is Atlanta here, this is LA, this is Chicago and Detroit, this is New York and Texas down here. So if we ever wanted any more proof that in the beginning, the importation, case importation is absolutely paramount important, and specifically through flights, this is it, right? So between here to here, it's clear what happens, and then look what happens a week later. Basically, it's red everywhere, because remember, the green ones were already red, so things are in full swing. So I think this is a very cool thing that we get essentially without doing much, without a lot of effort, just looking at re-looking at the population a different way. And then I think the last little policy inkling that we can get are very interesting cases is if you look at the way we have the consistent clusters here, right? These ones. So we can see that some states, for instance, California here in the West, is covered by a bunch of colors. Sorry, this is not a good, this is a picture, right? So you can see in California, we have a bunch of clusters, right? Kind of a bunch of them over the territory of California. Whereas, for instance, this green one here seems to kind of straddle New Mexico and the part of Texas, right? Florida has kind of like two big core clusters and then some discounted counties and so on. And then there's one sort of big cluster here, right? Sort of Midwest, North, and Midwest together. So in other words, what more can we say if we're looking at things this way? So in California, for instance, we can plot two things. We can plot in blue the average, the cases, not the average, the cases per capita between January to June of actually all the way to December, really, because we have all of them. But you can see that the cases, state cases, right? Cases per capita would be what was reported all the time. So it would be the blue curve. But if you're looking in these other curves, we have the pink and the brown, which literally drive the cases, right? These are much higher cases than the average of whatever was state level reported. And these are clusters 18 and 30 and 42. So specifically this pink one and 42 is the brown one. 42, if you're probably having an inkling, is just two counties, is Los Angeles and Ventura, which are neighboring countries. So big populations there. Whereas the pink ones are Riverside and sort of more east California towards Arizona. So these two are disproportionately carrying the heavy load. So in terms of a policy, if you're a policymaker, you probably want to have this information, right? Not every part of California is done, it was the same, is done the same thing. So perhaps sometimes differentiating or looking at things more granularly is a good thing. In Florida, we see that we have only two clusters that mostly make most of the state. But if you look at cluster 31, the blue, you can see which one that is. It's actually the the East Coast, particularly it contains Miami-Dade and contains Orange County. So it contains really the biggest urban areas of Florida. And if you look at the cluster 31, has by far, carries a much higher load than the state reported numbers, which are in green. Finally, the last thing is the situation in New Mexico, which is now in black, just to differentiate, and about half of Mexico, half of Texas actually in blue, and and a little bit of Colorado up here. And these guys make one cluster for us. So this is a situation where the cluster covers, it's a pan state, right? So if you're looking at the per capita epidemiology, I see that New Mexico is actually not doing badly for most of the year, except towards the end of 2020. Texas is clearly raising the bar, so to speak, in this cluster, and then the whole cluster is somewhere in the middle. So this seems to kind of illustrate, I think, from a policy perspective, the idea that while some states perhaps are well advised to look granularly to subpopulations in that state, others perhaps are better served by really coordinating and collaborating on policy, because it seems that their populations are so interrelated and interconnected that whatever perhaps New Mexico has been doing at that time would have worked better if also Texas would have been more cooperative, or would be more of a cooperative sort of policy implementation. To convince you that this is a framework and not just the one-off model that we build specifically for the purpose of, this data in the US, we have switched around and we use this algorithm to other regions. Specifically, we looked at Ontario. Ontario has 34 public health regions. And if you remember, each of our 34 public health regions had some sort of hodgepodge of public health measures. In some places, they were stronger. In some places, they were less strong. It was a continual fly-by-night sort of dates and deadlines and lifting and reimposing. And so we thought that we should try and recast this in larger subregions to look for some similarities. However, we did not have the proprietary data that we had in the US. We asked the company, we tried to acquire it, but they simply just did not collect it for Canada. So, that's that. But instead, we have looked to use Google Mobility and Work Mobility from Statistics Canada 2016, a survey of the labor force. And so we used these kinds of mobility, this sort of traveling for work and Google Mobility combination. And so what we got out of Ontario, we got this particular clustering structure where you can see it's one large cluster at the north, which makes sense. This is Algoma, Sudbury, and a whole load of very large public health regions, but are very sparsely populated. And then in the more colored parts here, we sort of show them a bit more zoomed in here. We have so we ended up having 8 clusters, plus the 9th being this big one, right? And so we can see that there's in terms of how people move around, we have the blue here, the eastern part, and then in the middle we have the Toronto, the Niagara, I think, region here, where we have the border crossing, of course, which is important, Toronto region, and so on. So the bottom line is that we can use the framework with different regional structures and counties and so on, different geographic regions, and slightly different takes on intermobility, right? And however we end up defining that. So we ended up formulating a new clustering algorithm. We looked for consistency. We defined the consistency in clustering for about 6 months, and the same definition could be extended, of course. We captured some spatial temporal spread of COVID-19 across the USA with an eye on what can we see that we haven't seen before. So we've seen the aerial importance and the fact that looking at state level data is misleading, because you might already have a lot of R0s ready to explode, but you just don't know about them, so you're reassuring yourself that you're fine. And we captured hot zones across the US. Sometimes the hot zones are are sub-regions of the state that could be important for future policy making. And then we show the algorithm is flexible, can be applied to other things. So thank you very much. I will stop here, and I'm happy to answer questions.